The ones in the class, this is your notes for section 8.5, Determinants and Cramer's rule. So what we're going to find out in this section is how to evaluate a determinant for a square matrix. Square matrix meaning there are as many rows as there are columns. So 2 by 2 meaning 2 rows, 2 columns. And then further we can talk about 3 by 3, 4 by 4, 5 by 5. But it has to have the same number of rows as columns if you're going to come up with a determinant. Alright, so the way we come up with the determinant here for a 2 by 2 matrix, I'm going to use a highlighter here to show you, is we multiply diagonally here A1 times B2. Alright, those two get multiplied together. And then we go multiply back the other direction diagonally, or what I refer to as the off diagonal, B1 times A2. Okay, or A2 times B1, if you want to keep it alphabetical order. And we subtract those two. So subtract those two products, and always the main diagonal, upper left, bottom right, minus the off diagonal, upper right, bottom left. So once you subtract that, that's the determinant of the 2 by 2 matrix. Okay, and then let's practice a couple of these, just evaluating it. So I'm going to multiply, go back to yellow, 5 times 3, so that's 15. And then I'm going to multiply the off diagonal, 6 times 7, which is 42, and I'm going to multiply those together. So 5 times 3 is 15, minus 6 times 7 is 42, and then 15 minus 42 is a negative 27. Alright, then B, let's do 2 times negative 5. So 2 times negative 5 is negative 10, minus, and then I come back the other way. 4 times negative 3 is negative 12. Okay, you always subtract these, so when you have minus a minus, you end up changing that to plus. So negative 10 plus 12 is 2. So there's the determinant of these two matrices. Alright, the question everybody always asks is, can your calculator do a determinant? And the answer is yes. If you recall, when we go through and set up our determinants before, when we came over here to math to find RREF, most of the time we just start scrolling up because it's easier to get to REF and RREF by scrolling up. But if you look, well, as soon as you go to math, DET, that's the determinant. So I'm going to go back and go back to this first matrix, and I'm going to change it to a 2 by 2, and I'm going to type in 5, 6, 7, 3. Alright, so there it is, 5, 6, 7, 3, that's my matrix A. I'm going to quit, come back in, go to math, determinant, and then come back in and say find the determinant of matrix A, and hit enter, and there's the negative 27. Okay, and then I can go back and edit that 2 by 2, put in 2, 4, negative 3, and negative 5, come back. The last thing I did was determinant A, so I just hit enter. I'll do it again, so there's the 2 right there. Okay, so your calculator can do determinants. It's just that DET underneath the math column. Alright, solving systems using determinants. So what I'm going to do here, I'm going to do two things. One, I'm going to notice that if I do like an augmented matrix, just over here on this side, this left-hand side, if I make a matrix out of just the left side, I get A1, B1, A2, and B2. Okay, so there's a matrix of the left-hand side. Alright, now what's the determinant of that matrix? Well, again, multiply these two together, you'd get A1 times B2, and then you subtract these two, so minus A2 times B1. So I'm going to put that there. That's going to be kind of important. I'm just going to stick that down here on the bottom of the page. And now I'm going to just go ahead and solve this system with not substitution, but elimination. I mean, I'm going to get a sign change here for y, and then solve for x. So to get a sign change for y, I need to multiply this top equation right here by a negative b2, right, or negative a positive b2, and then this one by a negative b1. I just need to get a sign change. So I'm going to do the top equation by b2. So I'm going to get a1 B2, okay, X. And then here I'll have a B1, B2, Y. Alright, and then I'll have a B2, C1. Okay, and then down here, I just multiply this top equation by B2. So I just multiplied everything through by whatever this number is in front of Y. And then down here, to get the sign change, I'm going to multiply the bottom one by negative B1. Okay, so now I'll have a sign change. I'll have a minus B1, B2, and a positive B1, B2. So A2 times negative B1 is negative A2 B1X. And then a minus, because it's a negative, B1 times B2Y. And that equals, and over here I got a negative B1 times C2. So negative B1 C2. Alright, now when I add these two equations together, what's going to happen? There's that sign change. B1, B2Y, negative B1, B2Y. So they're all gone. Here I have an A1, B2X plus, or minus, because it's a negative, A2, B1X. And then that equals, since there's nothing here for the y's, that equals these two. So B2, C1 minus B1, C2. Alright, now we're almost done. I'm going to factor this x out because I'm solving for x, okay, in the system. So I'd factor this x out. Now the last step, I'm going to divide both sides by the number x is being multiplied by. This is just like you would do if this were any equation. When you're solving for x and it's being multiplied by something, you divide both sides by that thing. So I end up with x equals this. And there's my solution for x. Okay, now you may be thinking, well, you know, whoop-de-doo, what is that? Look at all this jargon. But go back and look what we started off with. This was the left-hand side, right? This was the left-hand matrix, and if I blow it up again, A1, B1, A2, B2, those are the numbers in front of x and y. The determinant of that matrix, A1, B2 minus A2, B1, is that denominator right there. Now, interestingly enough, the numerator is also a determinant, but it's a little bit trickier to see. But B2, C1, B1, C2 has that kind of look too, where like the numbers kind of flip-flop. Well, where that's going to come from, this B2, C1, B1, C2, it's going to come from replacing A1 and A2 right here in this original matrix with C1 and C2, the original right-hand side. So if I put a C1 and a C2 here, what's the determinant of this matrix? It's C1, B2, right? It's kind of backwards, C1, B2, minus B1, C2, minus B1, C2. So there it is. That other matrix, like replacing these two in the matrix, these two ends up being that numerator, and the original matrix determinant is the denominator. So that will always work, and we can show, you know, extending this process further and solving for y gets a little bit tedious. Well, we could show the same thing happens with y, that we can solve it with a matrix determinant and divide one by the other. So what we end up with is, if we take the determinant of these original systems, the left-hand side, only the x and y coordinates, ignoring the constants, that will always be the denominator. And then replacing the x coefficients with the constants in your numerator and dividing those two determinants will solve the system for x, and then replacing the y coefficients with the constants and coming up with that determinant dividing by the original determinant will give you the y coordinate of the intersection, or the solution to the system. So it's a strange process. It's kind of peculiar at first, but this is Cramer's rule. Cramer's rule says if this is your system, you need to make 3 matrices and 3 determinants. So the first one, probably the most important one, is the original matrix because it shows up in both. And that's from the original left-hand side. Matrix number 2 is what you're going to use to solve for x. It's the numerator of the x solution. It comes from the constants in front of the y coordinates. So these in front, these in behind. So it's basically like you replace the x coordinates, or sorry, the x coefficients with the constants. So you're moving those, the b1 and b2 are still there, but you're moving these constants in place of where the x's were, and that's when you're solving for x. And then the last is when you're solving for y. So again, you're going to use the constants, but you're going to replace, instead of the x's this time, you're going to replace the y's. So a1 and a2 are there from the original matrix, like these denominators, but you're going to put the constants in the place where the y's were. So instead of a1b1, now it's a1c1. Okay, so whatever variable you're solving for is the position that gets replaced from this original matrix. So the left-hand side, the original coefficient matrix, if you want to call it that, that's always your denominator. And then you replace one column, the x's or the y's, with whatever the constants are in for the variable you're solving for. So if I'm solving for x, I'm replacing the x's, the a's in this case, with the constants. If I'm solving for y, I'm replacing the y coefficients, the b's in this case, with the constants. Alright, it's kind of weird to do it first, but once you get the idea, it's a very easy method to do because the matrix determinant is very easy to compute. Alright, so let's practice it. Use Cramer's rule to solve this system. Again, this is your last of the methods that you can do by hand when you're solving a system. One of your questions on your final is going to say, solve this system by hand, show your work. Cramer's rule was perfectly fine. So I call it D, like for the denominator matrix. So that's just the original left-hand side, the stuff in all black there. So I'm going to do 5, -4, 6, -5. Alright, and then I'm going to compute that. That's 5 times -5 is -25 minus 6 times -4 is -24. So -25 plus 24 is -1. So there's the denominator, right? This is this down here. So it was always -1 in the example that I'm doing now. Alright, then I put a little x for the subscript when I'm doing the x. So I'm going to replace 5 and 6 with 2 and 1. So this matrix is going to look like 2, -4. Okay, because it's the x position. 1, -5. So I just took this 5 and 6 that was originally there, threw it out, and replaced it with the 2 and 1. Alright, and now multiply here, I get a -10. Minus, multiply this way, I get a -4. So -10 plus 4 is -6. Alright, so that is this part. So that's -6. So what have we done? We just solved it. X equals -6 divided by -1. So here x equals, I'm going to put dx over d, which is -6 over -1, which is just 6. So I know the x coordinate is 6. I can do one, I can plug that 6 in and solve for y, since I know that's how it works, but I also can go ahead and complete Cramer's rule, do y. So make the matrix for y by going back now. 5 and 6 are back. Well, we're going to replace the y. So 5 and 6 are back. We're going to replace the -4 and -5 with 2 and 1 now. Okay, 5 times 1 is 5, minus 6 times 2 is 12. 5 minus 12 is -7. So that's y, or that's the dy, that's this one. So divide, again, I got that solved for now. Y is equal to that dy matrix, which is -7's added that as its determinant, divided by the negative 1, which is positive 7. So according to Cramer's rule, our solution should be 6, 7, and we can plug it in there and show that it works. Okay, 5 times x, which is 6, 5 times 6 is 30, minus 4 times 7 is 28, minus 4 times 7 is 28 is 2. So we do get a 2. And then 6 times 6 is 36, minus 5 times 7 is 35. 36 minus 35 is 1. So that is the solution to the system. And that's what Cramer's rule showed us it would be. Alright, what if it is a 3 by 3 system? Or a 3 by 4 augmented matrix, which makes a 3 by 3 system. So you need to be able to come up with the determinant of a 3 by 3 matrix, which is a little bit trickier. Okay, I'm going to show you 2 different ways to do it. But the way we do it is just kind of the way we did 3 by 3 systems before. We reduced it down to a 2 by 2. When we're finding a determinant of a 3 by 3, we do the same thing. We reduce it down to 2 by 2s eventually. So the way this works is you pull off one of these numbers in this first column, the x coefficients. Okay, so I'm going to pull off, let's say I pull off this A1. I'm going to put it there. Now, if I'm in this position, if I've got A1, I'm going to kind of ignore everything in that row and ignore everything in that column. And when I do, what am I left with? I'm left with these 4 numbers right here, which is B2, C2, B3, and C3. And then I treat that as its own mini little 2 by 2 matrix, and I find its determinant. Multiply these two together, subtract, multiply these two together. Okay, now once I've done that, I shift things down to A2. Okay, and when I do that, A2 is by itself, but we do subtract. Once we do like positive, negative, positive. We subtract here, right? And again, I rule out everything above and below and everything else on that row. Everything on that same column, everything else on that same row. And I end up with B1, C1, B3, C3. Okay, and then I do the determinant of this little matrix. Right, this gives me a number. This is a number times the matrix determinant's a number. So a number times a number minus a number times a number. And then we're back to plus. Okay, and then whatever A3 is, same thing. We're going to shift this down, shift this down. So now we're going to zero out everything again above, everything out to the side. And I'm left with this 2 by 2 matrix. B1, C1, B2, C2. And then the A3 gets multiplied by it. So it's kind of like we make these little smaller 2 by 2 matrices by eliminating a row and a column based on one number in this first column. Okay? And then this will give us a determinant. This is going to be the determinant of this 3 by 3 matrix. You just have to get the sign changed down. This A1, whatever sign A1 is, you keep that sign. Here, whatever A2 is, you change the sign. So if this were, a negative 3, this would be positive 3 or plus 3 times. So you just change the sign. Where it's the pluses or there is no negative, you keep whatever sign of this thing. All right, you could also do this across the top. All right, a lot of textbooks will have, instead of A1, A2, A3 going across here, they'll have A1, B1, C1. And then you would do the same thing. If I was going across the top and using this, I would eliminate this and this, and my matrix would be B1 times A2, A3, C2, C3. All right, so you could do it that way as well. You could go across the top instead of down the column, but whichever way, your goal is to kind of go down to a 2 by 2 matrix and use the methods that we just did to find the determinant of the 2 by 2 matrix. All right, let's do one. Oh, there's Cramer's rule. So Cramer's rule applies here. It's just one more extension. You find the determinant of the left-hand side. Okay, this is D. This is the D matrix just over here. And then you do the same thing. You want to solve for X, you replace the A's with the D's. You want to solve for Y, you replace the B's with the D's. You want to solve for C, you replace, Z, you replace the C's with D's. So we'll go through that process after we practice coming up with a determinant, a 3x3 determinant. So there's where D, dx, dy, dz get their name. So there's the original, just a coefficient matrix. And then you replace x. All right, I'm solving for x. I replace x column with the constants. When I'm solving for y, I replace the y column with the constants. And when I'm solving for z, I replace the z column with the constants. So let's come up with the, first of all, let's just come up with D. Let's take little baby steps into this. D is going to be equal to the coefficient matrix, or I should say the determinant of the coefficient matrix. Okay, so here's our coefficient matrix. Now, I'm going to show you what that last page meant. So I'm going to take this first position, this 3 right here, and I'm going to multiply that by, what do I eliminate? I eliminate the 2 and the 1, the negative 2 and 1 this way. So this is the matrix that remains. There's a little 2x2 matrix, 3, negative 1, and then 4, 3. Okay, that's positive. Now, go ahead and put the minus in there. Even if the next number is negative, go ahead and put a minus in there to remind you to do it. That's what everybody forgets to do. Okay, now I'm going to go down the column. So the next number is a 2. So minus 2 times, right? And then what would be eliminated here is same number, same column. So the 3 and the 1 are eliminated. This time it's the middle row. And I'm left with negative 2, 1, 4, 3. Alright, and then finally move down to the last position in that first column. So from the 2 down to the 1, I'm going to eliminate everything above it and out to the side. So a 1 is going to be in that last position. We do go back to keeping the same sign, so this is a plus 1 times, and then the matrix that remains is negative 2, 1. Alright, 3, negative 1. Okay, now, this is a matrix determinant, so 3 times 3 is 9. 9 minus negative 4. So 3 times 9 minus negative 4 would be 9 plus 4. Minus 2 times negative 2 times 3 is negative 6. And then negative 6 minus 4. Coming back this way. Remember, we always subtract, coming back the other way. And then plus 1 times, parentheses, negative times a negative is a positive 2 minus 1 times 3 is 3. So this is 3 times 13. This is a negative 10 times negative 2 would be a negative, I'll just do it, negative 2 times negative 10. I'll add it all up in the next step. 2 minus 3 is negative 1, so plus 1 times negative 1 is just negative 1. So that's a 39. Negative times a negative is a positive 20. Plus negative 1 would be the same thing as minus 1. So that's a 39 and 20 is 59 minus 1 is 58. So there's my determinant. Alright, and you can do the same thing as before. You can edit. I already got this one in there as a 3x3. You can put this matrix in as a 3x3 and then go back and do determinant. Okay, so we see the determinant is 58. Alright, so you can use that to check. If it tells you to do it by hand, though, again, you need to be able to show me that you can do this process. Alright, again, I'm going to keep a little note over here to the side. D equals 58. Okay, now I'm going to change this to dx. Okay, if I'm doing dx, that means I'm going to replace column number 1 with the coefficients. Sorry, the constants. So I'm going to put the 16, the negative 9, and the 2, I use red, in that position. Now, the nice thing about it is, because I'm using this column, is these other matrices are all going to stay the same. So all I need to do for the next one is replace 3 with 16. Alright, the 2 with negative 9, and then the 1 with the 2. Alright, all the way through this work. Alright, 16 times 13 plus, that's a negative 9 times a, sorry, negative 10 times a 9, that's a negative 90. And then negative 1 times 2 is negative 2. Alright, and that's a 208 minus 92, which equals 116. Okay, so that's dx. Alright, and then I'm going to go through the same thing. I'm going to just keep moving this over, going back to the original matrix to get dy and dz. Alright, so going through the last two and doing the same process, building the original coefficient matrix for x, y, and z, just replacing y with these constants. Okay, and then for z, the z matrix, replacing z, the z column with these constants. Finding those determinants, okay, I end up with these numbers. Now, remember the solution says x equals this dx matrix determinant divided by the d matrix determinant. So it equals 116 over 58, which is 2. Okay, so our solutions look something like comma, between parentheses 2 comma, and then for y, we have the y determinant over d. So that's this negative 174 over 58. Right, and if you do that division, you end up with a negative 3. And then finally 232 for z, we get dz over d, which is 232 over 58. Alright, all of them have the same original matrix as its determinant as its denominator. And then 232 divided by 58 is 4. So there's our proposed solutions. Again, plugging in and checking, you'll see that it works. 2 times 3 is 6, minus 2 times negative 3 is plus 6, plus z is 4. 6 and 6 is 12, plus 4 is 16. So it's going to work. It's going to work on all three. You can verify it with a RREF on an augmented matrix of this original form and see that it works. Okay, so Cramer's rule is perfectly fine for you to show your work and do that. Now, I do want to show you one last thing, another method to find the determinant of these matrices. So the first method was taking the number from the first column and then making the other 2 by 2 matrix from the things that are eliminated by that row and column. Another way you can do that is kind of an extension of the 2 by 2 form. You can go diagonal like you were talking about before. The only problem is you run out of room when you do that. When you talk about multiplying this way and then going back this way, or there's all these numbers that don't get multiplied by. Like for instance, if I mean multiply these together and then go back on the off diagonal, multiply these together. Well, there's a negative 2, a 2, a negative 9, a 4 that don't even get touched in the calculation. So what we do here is we copy the first column out to the side. So this 3, 2, and 1. And then we copy the middle column right beside that again. It's like the very first 2 columns get copied again. And what we do is we multiply diagonally this way all the way through until we get to that 16. So every piece on the top has been multiplied from upper left to bottom right. All right, and then we do the same thing with the diagonal going back in the opposite way, meaning that we start with the 16 and go down, but we keep going, we get to 3, and we make sure everybody on the bottom row gets included. Okay, now you may be saying, well, what about this 2? It didn't get hit. Well, it did. It got hit right there. Okay, and this 3 got hit right there. Okay, we extend it really just to make sure that everybody gets accounted for in this multiplication. Now, just like when we did the 2 by 2 matrices and then we went upper left to bottom right, those were positive. Upper right to bottom left, those were negative. So when I multiply here and I get 3, 3, 2 multiplied together. That's positive. That's considered plus. These are added. So plus, if it's in yellow, it's plus. Negative 2, negative 9, and 1 gets multiplied together. And then it's plus because this last one is also positive. It gets yellow. So the yellow again are positive. 16, 2, and 4. Alright, all that gets added. Now coming back the other way, in the blue color, that's negative. That's subtract. So minus 6 times 3, or 16 times 3 times 1. And then minus, this one is a 3 times negative 9 times 4. Alright, and this one's also minus because it's in blue. Negative 2, 2, and 2. Alright, 3 times 3 is 9. 9 times 2 is 18. Plus, negative times negative is a positive, another 18. And then 16 times 2 times 4, that'll be 8 times 628. And then minus, this is an 18. I'm sorry, this is a 48. And a negative times a negative is a positive. And then 9 times 3 is 27 times 4, 8. And then a negative times a negative is also a positive. 2 times 2 times 2 is 8. Alright, and then add all those together. Alright, I add all that together. I get 232. And that is what I got last time. Okay, and again, you can check it with your calculator. Okay, but both of these are two different methods to do the same thing. This method, when you're pulling the first column and making the smaller submatrices from it, it's perfectly fine. It's the exact same thing as this, right? The positives, the positive numbers going upper left to bottom right, the negatives going from upper right to bottom left. Both of those give you the same thing. It's just two different methods to do the same. So click view an example, you're going to see this method, but this is perfectly fine as well. So either way, you'll get the same determinants. It's just up to you how you want to do that. Now once you get the determinants again, it's division. All right, you divide to come up with these things. Okay, you divide to get x, y, and z, but you do need to come up with those determinants to be able to do it. Okay, get those determinants to be able to do them by hand, but also know that you can use that DET feature on the calculator to check, make sure you're doing it right.